We were founded as a company Belenos in 2008, and since then we work on fuel cells, and also since then we work together with the Paul Institute. First, we only worked on fuel cells running on hydrogen and oxygen. We even made a demo car with that. And then since 2011, we also work on fuel cells running on hydrogen air. But we still do work on fuel cells with hydrogen and oxygen, and I will show you why. In 2014, the owner of Belenos, or the Swatch Group, has decided that they don't want to continue this development, or that they don't want to continue this support of this development. And so we tried to find a new financing structure, and this has been completed now in this summer. So since July 2015, we now work as Swiss Hydrogen. We are still based in Mara, not as it's mentioned there in Biel, but it's not too far from Biel. Our product portfolio is, we have two fuel cells, or two fuel cell designs. One is our own design with using graphite bipolar plates. And there we have two versions out of that. One is a hydrogen oxygen fuel cell, and this we mainly want to use in stationary applications. And the other one is the hydrogen air fuel cell, which uses the same bipolar plate but different MEAs, and this is used in mobile applications. Here the power, this is for our more smaller power range, and then we have a third fuel cell that we can offer, and this is coming from a European project that we participate in, and this is called Autospec Core, and there we will have fuel cells with metallic bipolar plates, and then for the higher power range of up to 100 kilowatt. So the applications again for the hydrogen oxygen fuel cell is clearly stationary, UPS, uninterruptible power supply, gas to power systems, smart grids, island grids. On mobile applications can be range extenders or hybrid fuel cell systems for cars, buses, trucks, boats. So for mobile applications, of course, what is most important is the energy density. We all know that this is the biggest problem today when you buy electric cars is their range, especially in winter. Sometimes the range drops down to less than 100 kilometers, and of course this is not really acceptable. So what we need is we need to carry on more energy in a car, and we believe that there the fuel cell is a very good approach, and of course we are not the only one who believe that. Here's a comparison of energy density with power density, and you can see that that the lithium battery is today certainly the best technology that is available in battery technologies. But when you use hydrogen, you can realize much higher energy densities, and you still have very good power densities. So this is curves calculated with the system based on this Autostack technology with 100 kilowatt, and then calculated for different storage sizes. Of course, this is now takes into account the fuel cell system plus the hydrogen gas storage, which is the fair comparison to a battery, which of course contains both the energy and the power. So you can see that we can be almost a magnitude better than a lithium battery when there is a big system, like for example for a bus. The Post Auto here carries about 30 kilograms. Of course, for a smaller system with less hydrogen, the advantage is less. So certainly, heavy mobility, buses, trucks, is a very interesting application for fuel cell systems. Concerning this fuel cell developed in this European project, I want to present that here because it's, I think, a very interesting technology now. As I say, this is based on stamped stainless steel bipolar plates. It is fuel cell, PEM fuel cell with active area of 300 square centimeters. And what is, there's the first evolution that has been realized, picture is here, and the second evolution will be available as a full system in 2016, in June probably. And with this technology, we will reach a volumetric power density of 3.7 kilowatt per liter and a gravimetric power density of 3. This is even about 30% above what has been realized in the Toyota Mirai, which probably today is the best fuel cell that has been realized. So I think this might be really a world record fuel cell that we are going to develop there in this project. How about the cost? Of course, today fuel cell systems made in very small quantities are still quite expensive. But there was this cost study that is part of this European project that we do that has been done on exactly this technology, and it's a bottom-up cost breakdown. It's not top-down that we define, okay, this is the target, and then we see how we can manage it. It is based on really the manufacturing processes, so I think it's quite a reliable statement. And this has been done now for a production volume of 30,000 fuel cells per year, which is, for automotive terms, of course, a quite small-scale production. Nobody would make a combustion engine at this volume. But it's probably some realistic volume for going into the market for a big car manufacturer. So this means at 100 kilowatt, it means about 3 gigawatt per year of fuel cell power. And then the cost comes to, and this is the sales cost from the fuel cell manufacturer to the OEM, so to the car manufacturer. This would be the manufacturing cost. So if you compare to DOE studies, they are always a manufacturing cost only. And the organizational cost, profit and scrap from the different tier 1 and tier 2 suppliers are not taken into account in these studies. So what you really have to look at is what pays the car manufacturer. And I mean, this looks very attractive. It's about 67 euros per kilowatt. It's about 6,600 euro for a 100 kilowatt stack, but of course for a car manufacturer, this figure is still too high. They expect to, I mean, a combustion engine is about, at this level, is about 2,000 at the same power. But at least we are coming close to it, and when these figures are reached, then it's a real good alternative also to batteries. What we have done at Belarus and now at Swiss Hydrogen is we have done this demonstration car. There's a support of the Federal Office of Energy of Switzerland, both in the realization of this car and also in the testing phase, which we are doing now. And so far we have now driven 85,000 kilometers. And what is quite interesting, we have only installed a 10 kilowatt fuel cell. In the beginning everybody said that's too small. But what you can see here, this is the statistic of the car. The average power demand that we have in daily driving is exactly these 10 kilowatts. So the important statement is here, you can really, when you make a range extender vehicle, and you still have a battery with a good power on board, you can make the fuel cell much smaller than you might think. And this is good for a bridging strategy when the fuel cell cost is still higher, and so that you can introduce fuel cells already, having the benefits of fuel cell, but without paying too much for it. So what we have realized here is we have doubled the range of the car. That is a lithium battery as well, with 200 kilometers of range. And we have doubled it, taking a fuel cell with 1.7 kilograms of hydrogen on board. So we have now an overall range of 400 kilometers under NEDC conditions. But as you know from these current discussions there, these driving test specification is not always reflecting the reality. So in realistic driving, we probably reach 300 to 350 kilometers with both the battery and the fuel cell. So concerning the mobile applications, it's clearly there are advantages of the lithium batteries. For small series, it's certainly the lower cost alternative compared to the fuel cell system. The operation cost is certainly lower because electricity is obviously cheaper than hydrogen, which you produce from electricity, or you should at least. And the power density can be higher depending on which cell type is chosen. On the fuel cell side, the advantages is that you will certainly see lower cost in large-scale production. Large scale there means something like 100, 500,000 units per year. The refueling time, of course, is only less than 3 minutes. So even the quickest quick charge battery cars now, they have at least half an hour of refueling time. And this then depends on ambient temperature and how much the battery is already preheated before you arrive at the filling station. Here it's a guaranteed, or it's not, it's independent from the conditions. You certainly have a higher energy density, I've shown that in detail. And of course, you have not not a reduction in performance when you drive in winter, which you always see in the battery. So summary is, in our perspective, emission-free mobility without compromises in the long-range driving behavior is only possible with a fuel cell. And of course, there are different possibilities. You can have a fuel cell with a pure, or you can make a car with a pure fuel cell, no battery. You can make a hybrid, you can make a range extender, or of course, you can make a battery electric vehicle. And it depends on the usage and on the infrastructure side, which is the best choice. And we believe that the combination of a range extender together with a range-optimized battery, that this can play a very important role in the transition phase, because then you can combine the advantages of both systems. Now to stationary application. So we all agree that we want to make hydrogen as one of the superheroes. Of course, there are different possibilities to re-electrify hydrogen, because in the end what we want to have is electricity, or at least we also want to have electricity. Of course, one possibility is to make big plants, combined cycle power plants, so if there's a gas turbine with hydrogen and there's a steam turbine. You can do that and you can reach very good efficiencies. But of course, you can only do that where you have the possibility to store a lot of energy, so for example, a salt cavern. And then, of course, you have to make a very big plant, so in the order of 30, 50, 100, or several hundred megawatts. So this is certainly a very good option. Then there is the possibility just to use a gas turbine, not making the combined cycle. Then you lose a lot of efficiency. So this might be an option for 10, 20, or 5 megawatt systems, but then the efficiency is quite poor. And this is only just the efficiency of the re-electrification. Not speaking about the efficiency of the generation. Then of course there is an internal combustion engine. Probably this is not really an option because the efficiency is really poor and you can only make quite small engines. At least that is what is being realized today. And then you have a fuel cell, of course. So there's the possibility to have a hydrogen air fuel cell. You can certainly make systems from several kilowatt to multi-megawatt by grouping fuel cell stacks. The efficiencies will be between 40 and 55%. It's very difficult to get above these 55%. When you use hydrogen oxygen, and this is now our approach for stationary systems, you can also make very scalable systems, several kilowatt to multi-megawatt, but your efficiency will be significantly higher. You can realize system efficiencies of 60 to 70% depending on the overall over the entire power range. And of course, these systems, they are also dynamic, because a big power plant is less dynamic. A fuel cell can be operated extremely in an extreme dynamic way. You can see that when you drive from Brook to the PSI. It's motivating on the So now the comparison of hydrogen oxygen fuel cell to hydrogen air. One of the biggest advantages, of course, the higher efficiency. I mentioned that. The other advantage is the lower cost. So first of all, you have a higher power density in terms of phase area. You have per square centimeter active material. You have more power, about twice as much, and this can reduce your cost because today about 80% of the cost of a fuel cell system is the active area. Sorry, of a fuel cell stack. And the fuel cell system depends on it's oxygen. The fuel cell stack is the biggest portion. If it's a hydrogen air system, you have a lot of cost by the surrounding systems like air compressors. The system can be very reliable. It's a very simple system, and it has very few moving parts. So this is certainly an advantage for UPS applications, but also for other gas-to-power applications. It can be started very fast, and it can be operated in a very modular way. So you can do a startup within a few seconds. There's no air compressor that has to be run. And of course, it can operate completely independent from air conditions. So if you want to make a system high in altitude, you will have no decrease in power, which you would have with a hydrogen air fuel cell. And of course, ambient temperature and humidity are also not impacting the fuel cell, and even polluted air would reduce the performance all of that. Of course, for stationary energy storage, we have to look at the scale. So this is a graph. This is the capacity, so the energy that is stored. And this is the time that you want to store that energy. And I took this from work at the University of Regensburg, so they made a comparison here with the town of Regensburg, or here with the town of Berlin. So this is, of course, the overall energy amount of all the households per year in these cases. So that shows you a little bit about the size. And of course, now a constant power line is something like that. So we think, of course, batteries, they are very good here, where you have quite quite short storage times that you want to have, operation times. And as I said, the ultimate solution for very big scale systems is certainly what the classical power to gas. So storing hydrogen in a cavern and then re-electrification with gas and steam. But we think with storing also the oxygen, we can close the gap between these two systems. So now I have a few examples. I mean, probably on the lower end, this would be something at 50 bar of storage, a little bit like this for hydrogen, and for oxygen the same, 2 meters of high. So this is quite a small system. And maybe the upper end is something that uses 3 hectare of tube storage. I will show that in the next slide, what that means. Here at the PSI, there is now a system that will be built up. That is the ESI platform. I think that was presented last time, and I will also have a slide on that later. And this is exactly here. So it's about 3 megawatt hours, and it stores enough energy for a little bit less than a day at full power. So what does it mean, 1 gigawatt electrical energy stored in hydrogen and oxygen? I tried to do a comparison with the CNG storage in Urdorf, that is close to Zurich, close to Trier, to be exact. So they have I mean, this is Erdgas Zurich. They have I think it is one of the biggest natural gas storage sites in tube storages in Europe, and I think the biggest in Switzerland. They store about 700,000 cubic meters of natural gas, and they use a surface of a little bit more than 1 hectare for that. I found different values for the cost. It was always tricky, nobody wants to speak about that, but it's something between 16 and 25 million. If we want to store now 1 gigawatt hour electrical energy in hydrogen and oxygen, we need both here. We need a hydrogen storage and an oxygen storage. And the hydrogen is about the same size. It is a little less cubic meters, but natural gas has a better gas factor, whatever that is in here, compared to hydrogen. So we need, for less cubic meters at the same pressure level, we need a little bit longer tubes. So that would be the first hectare. And then oxygen is about half of that. So that would be, in overall, it would be 1.5 hectare of surface. That is assuming here 65% re-electrification efficiency, and using the same tubes as I used here. These are pipes for pipelines eventually. So if this can be done at a cost that is now extrapolated from here, we would achieve, I don't know that, we haven't done that yet, I think nobody has done that yet, we would achieve a storage cost of something around 30 Swiss francs per kilowatt hour electricity, which is certainly more expensive than a salt cavern, that is clear, but it is about a factor of 10 less expensive than a lithium ion battery today. Of course, now compared to on cell level, then the system, here's also the system, the fuel cell, but it's about this advantage that you can have. So when big amounts of energy has to be stored, we believe that this is an interesting option. Coming back to the PSI, there is now this energy storage integration platform where we want to deliver our fuel cell together. We want to develop together with the PSI and then install in the system until March next year. So you may have seen the container village already and the storage. So there's one container with an electrolyzer, and there's also one container with a fuel cell. here in this container, there will be 5 of these fuel cell stacks. Will be grouped together to a block of 300 kilowatt, and they will deliver then electricity and efficiency, and this is per stack now, so between 60 and 70%. The overall system, what you can see, is quite small. You can easily put it here on the table. And this will deliver 300 kilowatt. You can make a 500 kilowatt system maybe. So this is certainly a possibility to do modular system to go up to the megawatt scale. You can make 8 of these. 8 of these systems will make 500 kilowatts. So you need 2 times 8, and then you have a megawatt. So, summary on stationary applications. We think that our concept with hydrogen and oxygen storage can close the gap between battery storage systems and the large power-to-gas power plants. The hydrogen-oxygen fuel cell certainly has important advantages over hydrogen air. Of course, only when it's a stationary case, otherwise you have the problem that you have to carry around the oxygen. You only want that in very special environments, maybe like submarines or in space, where you have no air. And of course, when hydrogen, where does oxygen come? When hydrogen is produced from water electrolysis, and this is of course the choice of the future. The oxygen is a free byproduct. You just have to capture it and maybe compress it, maybe not. In the easy system, it's not even compressed because the electrolyzer delivers it directly at 50 bar, and then it's stored at 50 bar. But it's then a free byproduct, and you just have to take care of the extra storage. But then, of course, when you have a more efficient system, first of all, the electrolyzer can be smaller, and your hydrogen storage can be smaller. So the on-cost that you have on the oxygen is compensated by that, largely compensated by that. And then, knowing that the fuel cell system is also smaller, also less expensive, we are certain that there will be an overall system cost benefit. And we do this compared to a hydrogen storage only with the fuel cell system. That's my speech. Thank you very much for